Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we will conclude our discussion on KP model, and if time permits we will also discuss the notion of effective mass. Before going into these ideas, let's see what we did in last couple of classes, last couple of discussions. And as you might recall, we were discussing how an electron behaves in actual solids, and we considered the case of 1D solid, and a 1D solid has atomic arrangement, or to be more precise, atomic cores arranged in this way, and the potential profile, the potential energy of the electron due to two of these cores will look like this, and the potential energy of the electron because of the entire chain of atoms, because of the entire 1D solid will look something like this. And this is with this potential energy we need to solve the Schrodinger equation in order to precisely determine the behavior of electrons. Okay. And here we invoked the chronic Penny model, the KP model, so called KP model, which allows us to solve the Schrodinger equation for electrons in 1D solid precisely, but with a slightly different kind of potential profile. Here we avoid infinite infinities in the potential energy, and we take finite potential energy values, and the profile looks pretty much similar to what it is there in the actual solid, not exactly same but quite similar to that. And with this potential profile, we saw that by using Bloch's theorem, which essentially allows us to calculate the electronic wave function when we have periodic potential. By using Bloch's theorem, we can solve for the Schrodinger equation in this in the KP model potential energy. And this is what we were doing. We were after solving the Schrodinger equation, we used boundary conditions, and there were 4 unknowns in the Schrodinger equation, 2 equations actually, and there were 4 unknowns, and we used 4 boundary conditions, and 2 of these boundary conditions come from the continuity of the wave function and continuity of the derivative of the wave function, and the 2 other boundary conditions come from the statement of the Bloch's theorem, the statement of Bloch's theorem about the wave function, and the statement of Bloch's theorem about the derivative of the wave function. So this is the so given a periodic potential, this is the statement of the Bloch's theorem. An equivalent statement of Bloch's theorem is that in a periodic potential the wave function can be written as like a plane wave. Psi x is plane wave multiplied by a periodic function, where ux is a periodic function, which means ux is ux plus a, where a is the period of the potential energy. Okay. So these 2 statements of Bloch's theorem can be used interchangeably, and what we also observed here is that this parameter k comes from the Bloch's theorem, and it is the so called crystal momentum of the electron. Okay. So after solving these 4 boundary conditions, after solving for the coefficients in Schrodinger equation from the from these 4 boundary conditions, we finally came up with this constraint or this equation. The solution of this equation will give us the values of energy corresponding to a k value. Okay. So, on the left hand side we have a function which is which we have a function where the parameter is xi. So, on the left hand side there is a function of xi where xi is essentially E by u naught, where E is the energy, u naught is the potential from the chronic Penny model. On the right hand side we have a cosine function, and the cosine function has k in its parameter, basically cosine of k into a plus b. Okay. So, on the left hand side we have energy function, on the right hand side we have the k function, the crystal momentum function. So, in essence it will give us the energy corresponding to a given value of k. Okay. So, it will give us the E k relationship for the solids, in particular 1D solid. So, that is what we will see, and we will try to understand that. So, as I told you in the previous class as well, now because of the Bloch's theorem, by virtue of the Bloch's theorem, we just need to solve Schrodinger equation in one period of the potential in two regimes, regime A and regime B, and by using Bloch's theorem we could solve the Schrodinger equation, and finally this is the constraint that we came up with. So, on the left hand side we have a function which is which has coefficients as xi, parameter xi, and there is this hyperbolic terms as well. So, the mathematical solution would be slightly complicated, in fact it would take a lot of time to do the exact mathematical solution of this equation. So, that is why we resort to the graphical representation of the solution, and what we do is we plot f xi, which is essentially the left hand side function as a function of xi. Okay. And as you might have already realized that in order to plot this f xi function, we also need these parameter values, these system parameter values, so to say, these alpha naught a values, for example alpha b value. So, these alpha naught a, b, these three values we at least need to have. So, for a standard value of let us say alpha naught a, let us take it to be pi, and or we can take any arbitrary value of these constants, and then if we plot this function f xi as a function of xi, it will be something like this. It will be a hyperbolic function. Hyperbolic means that initially the amplitude is high, it starts with a high amplitude, but gradually the amplitude decays. So, gradually this is how this function typically would look like. So, this is the plot of the left hand side function, and as you might have already realized that on the right hand side we have a cosine function cos k into a plus b, and for an infinite crystal, for an infinite solid, this k can take any value. So, basically k will have continuous values. So, which means this right hand side function for an infinite 1D solid will be a function oscillating between +1 and -1. This can take any arbitrary value between +1 and -1 on the right hand side. On the left hand side, however, we have a hyperbolic function which can take values from which initially has high amplitude, but gradually the amplitude decays down. So, the E and K values which will jointly satisfy this equation, if we try to figure that out from this plot, those values will be those values of energy or those values of this parameter xi, which will make or which will for which this left hand side function is between +1 and -1. So, what I mean is that for those values of xi for which this LHS function, left hand side function, is between +1 and -1, for those values of xi we will have a valid k value, because the right hand side function can only take values between +1 and -1, it can only go from +1 to -1. So, those values of xi which makes the left hand side function greater than +1 or less than -1, they will not have any value, any k value corresponding to them. So, what it means is those energy values will not have any k value corresponding to them, which means those energy values are not permitted for the electrons. Electrons cannot occupy those energy levels, that is the physical intuition behind the solution of this equation. So, let us see it here. We have now plotted dotted lines between +1 and -1, and we now see that on the xi axis, in this range of xi values, and similarly in this range of xi values, the left hand side function is between +1 and -1. Similarly here, between these values of xi, also between these values of xi. So, this is not an exact plot, but this is a qualitative picture how the solutions of the Schrodinger equation exist in the according to the KP model, and we can see that there are certain xi values, which in other words mean there are certain energy values for which there exists a valid k, which means there exists a valid wave function, and there are certain other energy values for which there is no valid k, which means there is no valid wave function corresponding to those xi values. So, these highlighted portions on xi axis essentially are the xi values for which we have a valid k value, we have a valid crystal momentum for the electron. So, we can say that the electrons will occupy, or electrons can only occupy these energy values, and there are certain energy values which are prohibited for the electron. You might now correlate it directly to the idea of the bands and band gap, which most of you might already be familiar with. In solids, we have allowed energy bands where the electrons can occupy valid states, or we have a certain range of energy where electrons can take those energy values, and in the band gap the electron cannot exist, electron wave function cannot exist. So, those are the disallowed energy values for the electron in solids. And here also we can directly see that there are certain values of xi which are permitted for the electron, and there are certain values of xi which are not permitted for the electron. So, these permitted values, in other words, are the energy bands, the allowed energy bands, and these xi values where the electron cannot exist, these are the band gaps. So, similarly we can see it on the entire xi axis. Okay. So, if you recall our last few classes, a free particle, when the electron is totally free, it is not interacting with anybody in the universe, or it is as if it is the only thing in the universe, electron's energy is continuous, it can take any energy value. When the electron is confined in a potential well, it can only take discrete values. Okay? But now the potential profile is slightly complicated. Potential profile is periodic, and in periodic potential profile, electrons can take certain range of energy values and they are not allowed to take certain other ranges of energy values, and these are called the bands, energy bands and band gaps in a solid. So, the notion of bands and band gaps come directly from the solution of the Kp model, solution of the Schrodinger equation according to the Kp model. Okay, so that is actually the advantage of understanding the Kp model. It very clearly explains how the notion of bands and band gaps arise in the solids. Okay. So, with this understanding, we will go a little bit deeper now in order to understand how the electron actually behaves in solids. There are few other points. This is a slightly better plot of f xi as a function of xi, and as you can see here, it is clearly mentioned when we plot f xi as a function of xi, this function takes hyperbolic value, and there are certain energy values which are allowed for the electron, as is also clear in this plot. Okay. So, with this understanding, there are few more important points that we need to keep in mind while trying to understand electrons in solids, and those points have not been mathematically derived here because of the lack of time, I would say, and lack of and we did not intend to cover that in this course. But please keep those things in mind, and if you have time, please go through the derivation of Bloch's theorem, and these things will become quite obvious, or these things will naturally come from the derivation of the Bloch's theorem. Okay. So, a few important points that we need to keep in mind is that for 1D systems, only two distinct k values correspond to every energy values. So, in 1D solids, for every energy values, there are two k values which will give that energy value. Okay. So, if we go back to this constraint, for every xi value, there will be two k values which will give us a valid xi value. Okay. Second is, if the period of the potential profile is A, if the period of potential is capital A, then the k values, the values of k which differ by a multiple of 2 pi by A, this capital A, they give the same wave function for the electrons basically. Or in other words, the k values which are separated by 2 pi by A, they essentially give the same wave function, and that is a direct consequence of the Bloch's theorem, because if we look back to the Bloch's theorem, Bloch's theorem states that psi x plus A is essentially exponential I k times A, capital A, into psi x. So, this is the standard statement of the Bloch's theorem, and so instead of k, if we take k prime to be k plus 2 pi by A, and we put this value of k prime in this equation, and let us say the wave function now is psi prime, k prime is I k prime A psi x, and if we put k prime to be k plus 2 pi by A, capital A. So, this will essentially be exponential I k A times psi x into I 2 pi, which is essentially 1. This is 1. So, this turns out to be I k A psi x. So, which is psi x plus A. So, a k value shifted by 2 pi by A gives the same wave function essentially. Okay. What it means is that the complete set of k values is now in the range of 2 pi by A, 0 to 2 pi by A or minus pi by capital A to plus pi by capital A. Okay. So, the complete set of k values exist in the range of 2 pi by A, where A is the period of the potential profile. In our KP model discussion, the potential of the period of the potential profile was small a plus b. In that case, capital A was small a plus b. So, all the valid k values or complete set of k values will be between 0 to 2 pi by a plus b or minus pi by a plus b to plus pi by a plus b. Okay. And this is an important statement, please keep this in mind. This has a simple derivation as well. This is also clear from the mathematical form of the Bloch's theorem. The third point that we need to keep in mind is that if the crystal is assumed to be infinite in extent, in that case this k can be any real number. So, if the crystal is infinite or very long as compared to the dimensions, as compared to the distance between two atoms, in that case k can take any real number and there is no other constraint on k. And this we can see also from the statement of the Bloch's theorem. The statement of the Bloch's theorem says that the wave function can be written as I k x times u x, where u is a periodic function with the period of potential profile. Okay. This is sort of another statement of Bloch's theorem which we have discussed many times, and if the crystal is infinite in extent, which means this x can go from minus infinity to plus infinity, it can go from minus infinity to plus infinity. In that case, ux will be well defined because ux is a periodic function. It will be well defined over all the places if it is well defined in one period because of this virtue, because of its periodicity. A periodic function is defined everywhere. So, the only thing that needs to be well defined is this plane wave solution or this exponential I k x term, and this will be well defined if k is a real number, because if k becomes an imaginary number, in that case this exponential will blow up at infinities. Okay. So, if the crystal is extremely large as compared to the distance between two atomic cores, in that case k can be any real number. Another constraint is k can take values or complete set of k values can be obtained in the range of 0 to 2 pi by a. In other words, it also means is that if 2 k values are shifted by or 2 k values are located by 2 pi by a distance from each other, then the wave function corresponding to these 2 k values will be the same. Another point is that for finite crystals, generally this is just to keep in mind, when the crystals are finite, which is actually the case in most of our devices, we invoke what is known as the periodic boundary conditions, because practically speaking we do not have proper boundary conditions on the boundaries of the crystal, boundaries of our device, and these periodic boundary conditions give good approximation to the actual scenario. So, what is the periodic boundary condition? So, in a finite crystal, which means that now the crystal has n number of atoms, 1, 2, 3, 4 up to n minus 1, n number of atoms, atomic cores, and if the distance between each of them is a, then what we assume is that the wave function here, periodic boundary condition means that this is the period of the this n times a, the entire length of the crystal is the period of the wave function. What it means is that the wave function at this end of the crystal, this end of the solid and this end of the solid will be the same. What it means mathematically is psi x plus n a is equal to psi x. So, this is the periodic boundary conditions, and it gives for all practical purposes it gives good results. By results I mean the valid k values. So, so if we sort of do a slight analysis here, what this implies is from the Bloch's theorem we can say psi x plus n a would be, from this statement of the Bloch's theorem, psi x plus n a would be exponential I k times n a, psi x would be equal to psi x, because of the, according to periodic boundary condition, n a is also the period of the potential profile. So, the Bloch's theorem can be applied here as well, and what it implies is that exponential I k times n into a is 1, which basically means that k times n a, capital N a, would be 2 pi n, where n can be any integer. So, k is basically 2 pi n by n times a. So, the for finite crystals k will have discrete values, and these discrete values will depend on the length of the solid or length of the crystal itself, and a, the distance between two atoms, and this will be 2 pi by 2 k values will be separated by 2 pi by capital N times a, and this small n is can be any integer. And we can also see from here, if this capital N is extremely large as compared to small n, then this will be almost a continuous set, or sorry, if capital N is very large number, in that case this the distance between two k points will be this. So, this will be almost 0. So, which means that k will be continuous, k can take any continuous values, as is as we have already discussed in our previous slide. So, these were few more important points apart from the idea of the energy bands and band gap that arises out of the solution of KP model. These are few other points that we need to keep in mind while sort of trying to understand the electrons in solids. So, now extending our discussion of energy bands, generally it is the case that the energy bands, the notion of energy bands is mathematically clear to most of us, but it is not intuitively or physically clear to in our minds. And this is what we will try to see here. This is by no means is an actual plot, but this is how the bands look like in a solid. So, as we have already seen that the potential profile in a solid looks something like this. These are the, this is the potential energy of electron in a solid. Okay. Here are the atomic cores, and as we had already seen, close to the atomic cores, the potentials, the potential energy of electrons go to negative infinity. Okay. So, this is what we started with. These are the ends of the solid, and by making an approximation using KP model, we solved the Schrodinger equation, and we saw that there are certain energy values which the electron can take, and there are certain other energy values which the electron cannot take. Okay. So, if we picture that here in this particular potential profile, let us say if this energy value is allowed, we will have a range of energy values which are disallowed. So, for example, energies between this and this will be, these two levels will be disallowed. So, we will have this energy range which will be allowed. So, if the energy of the electron is less than this u naught value, this was the u naught value, it will have a discrete energy level, almost a discrete energy level. If the energy of E, the energy of electron E is greater than u naught, which is the peak of the this potential period, in that case there will be a range of energy values which is allowed, and there will be a range of energy values which will be disallowed. So, these are the allowed energy values, or this is the a valid electronic band in the solid, and these are the, this is the another band, another range of energy values allowed, and in between this is the disallowed range or the band gap in the solid, as is pictured here. Okay. So, this is the physical picture corresponding to the potential profile in a solid, physical picture of energy values of electrons in a valid energy values in a solid, in a 1D solid particularly. Okay. So, this brings us to the notion of Brillouin zone, which we will discuss after this, and I will discuss that in the next class, because that might take some more time. But I hope that in this class, how the bands and band gap arises in solids, that is now mathematically and intuitively clear to us. Thank you for your attention. I will see you in the next class.